For our Dynamics term project, we decided to tackle the Eaton Supercharger lift assist problem. The Athens, Georgia-based Eaton Supercharger facility has added 2 new product lines that require a new Gorbel bridge as well as a Gorbel lift assist. Our job was to determine the most cost-effective bridge and lift that can be used for the new products. Using a variety of dynamics equations we have acquired over the semester, we calculate the load ratings and then use those to compare models and determine the most cost-effective option. Pictured below is both the Gorbel G-Force Q-Series lift assist as well as the freestanding bridge crane, both needed for the new production lines. So the assumptions that we made were that we have 2 different production lines. Production line 1 has an end effector tare weight of 45 pounds and a capacity of 100 pounds, equaling up to a total of 145 pounds. The second production line has an end effector tare weight of 178 pounds and a capacity of 50 pounds, adding up to a total of 228 pounds. The weight of the lift assist is included in its capacity, and the acceleration value of the lift assist is a constant.
For our process, we began our analysis by determining the total capacity needed for each production line. For production line 1, we had a total weight of 145 pounds, which meant that the lift needed would be the Gorbel Q series rated at 165 pounds. For production line 2, we had a total weight of 222 pounds, which meant that the higher rated 330 pound Q series lift would have to be used. Once we determined which lifts were needed, we began calculating what the capacity of the bridge crane needed to be. Using specifications from Gorbel, we determined the velocity and travel distance of our chosen lifts. We also converted our weight to pound mass so that we could use them in our calculations. So for production line 1, our velocity was 3.33 feet per second, and it traveled a distance of 11 feet, and the mass was 4.508 pound mass. For production line 2, our velocity was 1.67 feet per second, and it traveled a distance of 11 feet as well, and the mass was 7.08 pound mass.
For our calculations, we started by finding the time required for the lift assist to move from the top to the bottom or the bottom to the top. So we took our entire travel distance of 11 feet and our initial velocities of 0 and our final velocity of 3.33 feet per second. Using these numbers, we found a time of 6.606 seconds. Once we used this, we found our acceleration by taking the distance as well as the time to find our acceleration. Once we had our acceleration, we used our pound mass values that we found earlier and combined them with the acceleration due to gravity as well as the acceleration due to the lift assist. Our pound force value for production line 1 was 147.43. For production line 2, our calculations remain the same. However, we subbed in 1.67 for our final velocity instead of the other 3.33 to find a time of 13.205 seconds. Using this time, we found an acceleration of 1.26 feet per second squared. Using this acceleration, again combining with gravity acceleration and the newly found pound mass of the second production line lift assist, we had a total pound force of 228.9. Based on our calculations, we determined that both production lines could be equipped with the 250-pound bridge cranes. This capacity would support both the calculated max loads while providing the most economical option. However, a 500-pound capacity crane could be used for the second production line as the max force was relatively close to the capacity of a 250-pound crane. However, this would cost more than using a 250-pound crane.